is a couple of minutes after 4. And our next speaker is Omar Fawzi from Lyon, and he will talk about compatibility problems in quantum information.
Thanks a lot for the invitation. So, yeah, I work in quantum information theory, and in recent years, I've been interested in many tools from optimization, and I'm going to talk about some results we obtained in the last few years. Some are quite old, that are like applying optimization theory to quantum information problems. So my objective here is to present some of the quantum information problems in which the tools you're used to here could be applicable. So and feel free to stop me. So I think it should not assume knowledge of quantum theory. But please feel free to stop me if there's something that is unclear. Okay, so I'm going to present two main results in this talk, and so they're both in this area of what I call algorithmic questions in quantum information. So usually when we think of quantum information, you think of quantum algorithms for solving some problems, like, for example, factoring or something. But here in this talk, I'm thinking something different. So the computational problem that we're looking at is inspired by quantum information. It's a problem that comes from quantum theory, but I'm going to look at classical algorithms for it. Okay, so this there's many classical algorithms when studying quantum information that are being studied. So I'll not talk about all of this, but so for those of you who know a little bit, so in the context of quantum error correction, which are crucial to build a quantum computer, so there is a lot of studies on what we call typically a decoding algorithm. So this is just an algorithm that takes as input the syndrome and outputs the potential error. Okay, so this is a fully classical algorithm. Okay, so what's a syndrome? Okay, yes. So in error correction, the typical way error correction works is that you perform some measurements, okay, and if there were no errors at all, the syndrome should be all 0.
What is a syndrome? What's the definition of syndrome?
What's the you mean mathematical definition of a syndrom? Okay.
That would make me happiest,
yes.
But I'll settle for anything.
Okay. So it's not super important for the rest of the talk, but I can give it to you. So
sorry, I didn't erase. I apologize.
Yeah.
My predecessor.
Okay, I think I need to introduce it. I'll set it for a classical code for now, but so if you have a code which is given by a parity check matrix, ask me a parity check matrix. No, this.
I'm okay with that.
So okay, so a code C is just a linear code C is defined as set of x's f to the n such that hx equal to 0. Okay, and so imagine you have an x which has some errors now. So now that you have x plus e. Okay, the syndrome is just the syndrome of this error is just h of x plus e. Of course, it's just h of e, and so for s. So this is what I call syndrome, and this problem that I mentioned here, which is
H is a vector and
H is a matrix.
Like n by m or?
Yeah, n by m. Yeah, so
which is larger?
So typically, so x is of size n, and m is smaller.
Okay,
so this is
compressing.
Yeah,
H compressing. Okay.
I don't see that really as this is the encoder. It's computing some parities, right? So for example, okay.
Right. Yeah,
yeah. Okay. So yeah, just the algorithm I'm talking about is given an E, or sorry, given S, you want to compute an E, which is a weight. that satisfies HE equals S. Okay, this is typical. It's a very standard computation problem in error correction. It's also important in quantum error correction. And so this is, we typically find classical algorithms for that. So something which is closer to what I'll discuss a bit more in the talk is, now I don't want to decode an error correction. I don't want to decode specifically an error, but I want to find an H which is good for my nose model. Okay, I'll discuss this a bit more in a minute. So then going to quantum complexity theory and non-locality, there was lots of discussion, or there was lots of work in studying from an algorithmic point of view. How do you simulate an interactive proof with entangled prover? Okay, so or in other words, maybe it's simpler that I say it this way. So I have a non-local game. So this is a game played between two parties which cooperate. Okay, and you can give them a resource which is that we call an entangled state. Okay, I'll define this in a few slides. So and then you want to compute what is the optimal strategy that we can have for playing this non-local game with this quantum strategy. Okay, so okay, another class of problems, which is the class of computation problems which even started this idea of quantum information, is the problems coming from quantum physics itself, right? So so there I have a quantum physical system, and I would like to predict some of its properties. Okay, so this defines a computational problem, and you can ask about the complexity of such. Okay, yeah, this is what I mentioned here. This is one of the first motivations to study quantum computers, or to consider quantum computers by Feynman and others. Okay, so yeah, as I said, so the outline of my talk, I'll have two parts. So the two parts are completely independent, actually. So this is a rather specific problem about. So I'll define the problem of noisy channel coding, and I would like to know what is the effect of entanglement for channel coding. Okay, so how much can entanglement help me in transmitting information over a noisy channel? And the second part of my talk will be more in the line of quantum simulation, about computing ground states or gift states of quantum systems. Okay, and the common theme between these two is the title of my talk. So you see that for these two problems, the main underlying question is to understand what are the observations that are compatible with the global quantum state. Okay, so there are no questions in this introduction. Let me get to the first question, and I will describe it precisely. So yeah, as I said, so the question here is about using a noisy channel for reliable communication, and it's classical communication. So the noisy channel is classical. Okay, so how do I describe a channel? So all my systems will be discrete in this talk. So a channel is just, I see it as a bunch of numbers, W of Y given X. So for every X, I have a probability over the possible outcomes. Okay, and so this just describes my channel. And what I would like to do is to send a message across, okay, from Alice to Bob. Okay, and so this message is going to be denoted by I, which is going to be a number from 1 to K. And our task here, okay, is given this W and this K, I would like to say I would like to design a system here which allows me to transmit information in the most reliable way possible. Okay, so as to increase the probability of successful transmission of I. Okay, so as you might know, so this is basically the fundamental problem that started the area which is now called information theory, as stated by Shannon. And so, yeah, so, okay, let us make this more mathematically precise. So, okay, so what will I allow on Alice's and Bob's side? So it's natural to allow the most general function, okay, that maps this message to my resource that I can use, this noisy channel. Okay, so this will be an encoding function. So it takes an I and it outputs an X. So a priori, it could be arbitrary, it could be randomized, right? So I have a probability of encoding, of given an I, of encoding this into X, and same thing for the decoder. Okay, and when will I consider this as a success is if what I decode gives me the same what I wanted to encode. Yes?
Could you put the encoder and the decoder both in the channel itself, or why you decompose it?
So, I mean, they play a different role, right? So you see that, okay, this channel is something you have, you cannot change it, right? So this is given to you, for example, think of it as a cable, okay? So it has a fixed error rate, okay? But you as a system designer, the thing you have access to is prepare an encoder and a decoder that uses this resource. So they play a different role. So that's why, okay, here I write this as an optimization problem. So W is given, think of W as fixed, and E and D are variables that I can use, that I can optimize on. Okay, yes, yes, so I would like to find ED that maximizes. Okay, so this I wrote it in terms of an optimization problem. You see here, it's not a linear problem. It's bilinear, so linear in E and D. Okay, so I mean, my objective would be to study this this optimization problem in a bit. But before, let me say, so I told you that this fundamental problem in information theory was well studied by Shannon. So he didn't look at it from this point of view of studying how to solve this optimization problem, but rather he formulated it in a slightly different way. So he said, okay, so this channel W that I have access to, I will take it of a specific form, right? Which is very well motivated, right? So I would say that this channel is not a completely arbitrary channel, but it's one which is sometimes called memoryless, or IID for simple. So it's just multiple copies of a simple basic channel. Okay, so the simplest possible thing is think of this small W as just a channel taking as input a bit and outputting another bit, okay, outputting an output bit. And so the simplest channel is, for example, imagine that you flip the bit with a probability P, okay? So if you do this independently, so now you can construct a channel on n bits that takes independently each bit and flips it with probability P, okay? So this gives me this memoryless channel, or for short, I call it IID channel. And what Shannon was able to do in his famous theorem is to characterize the optimal encoding and decoding as n goes to infinity. Okay, so in the notation that I introduced in the previous slide, Shannon's theorem is stated as follows. Okay, so what I want to study is this optimal success probability. Okay, so for W tensor n, so think of W as this just one bit channel that you flip with some probability. Okay, and of course, as n grows, the messages that you can transmit will be more, right? So you can transmit more by using more of a given resource. So it's natural to look at the message set. Remember, the message set that I want to transmit as also something that grows exponentially with n. Right? Okay, so I mean, yeah. So if you think of it like k or log of k is the number of bits that you can transmit per channel use. Okay, and so what Shannon proved is that this success probability it undergoes some threshold, say, so for some value of k, and this value of k is called the capacity. Okay, so Okay, so let me introduce this notion of capacity. So this is some information theoretic. This is some entropic quantity that measures the correlations between the input and the output of this channel. Okay, the exact definition of I here doesn't matter for this talk because I won't talk about it more. But for those who know, this is the mutual information. Okay, so this is a measure of correlation between X and Y. Of course, W only gives me given X what is the output. So I have to specify an input distribution in order to have a joint distribution X and Y. Okay, so actually the formula tells you that you should maximize over all possible input distributions. Okay, so you maximize over all input distributions. This now defines a joint distribution X and Y. Okay, just like this. And then you measure the mutual information.
Sorry, K is like the message that you did on this simple channel.
Yes.
Okay.
So yes, K is the it's the but here it's the number of messages if you want per channel use.
You can start with K instead of K to the end, you can take K1 to 2.
Yes, but you don't distinguish, right? So what you see is just W n times, and you want to send K to the n messages. So the different messages don't play a different role, right? So
K is the out. Yeah. K is off the number of letters.
Yeah.
okay, sorry, K is?
The number
K is the length of your alphabet.
Yes, exactly. Yeah. K is a number. Yeah. Yes. Okay, so is this so Shannon's theorem, it tells you that there is this number. So if you compute this capacity, if you try to transmit below the capacity, then you can get the success probability to 1. And if you try to go beyond the capacity, then the success probability goes to 0. Okay, so I assume many of you would have seen this theorem. If not, then I think probably maybe that's the most important part of my talk that you've seen. I mean, the first time I've seen Shannon's theorem, I think it was. I thought, it was one of the most beautiful theorems I've seen. So it's amazing that we can actually characterize this limit. Okay, so
Also, a comment. It's also one of the best written mathematics papers I've ever seen. So even today, it's better to read this paper than anything else. Really good.
So just the technical thing is that this part was not shown explicitly as is by Shannon. He just showed that this is strictly smaller than 1, but the Sharp's threshold was shown a few years later. Okay, okay, so this is what I would call the statistical point of view, where you take your resource, you take n copies of it, and you take it as n goes to infinity and study in the limit as n goes to infinity, what can you say about the optimal rates you can achieve? Okay, so in this talk, I'll look at a slightly different point of view. So I put it here. So where my channel is something general, okay, not necessarily these multiple copies. And what I'll try to discuss is more, so I'm motivated by two things. I would like to compute this quantity, let's say, for a given W and K. And I would like, actually, really, the question that brought me to this is the effect of quantum entanglement on this question. Okay, so let me introduce that. Okay, so now I ask exactly the same question. Okay, so I would like to transmit a message, but now I allow myself an additional resource. Okay, an additional quantum resource. So far, it's a fully classical problem, but I allow myself an additional resource, which is a quantum state, which is shared between Alice and Bob. Okay, so let me tell you how this is modeled. So this is modeled by, I give myself a Hilbert space, okay, for Alice and one for Bob. So it will be the same one. I'll denote it by H here. And so they will share some quantum state. So which I'll denote by psi here. Okay, so this is the vector in this tensor product of these two Hilbert spaces. And okay, so if you want, think of it as a general, for now, for simplicity, think of it as a generalization of shared randomness. Okay, so imagine that Alice and Bob, they can, in principle, share a random bit between themselves and try to use them in their encoding and decoder. So this is a sort of generalization of it, where they hold the quantum state, right, psi, or in the tensor product Hilbert space. And so, but now what do we do with it? Okay, so now what we do with it is that instead of having this this randomized algorithm which map I to X, now this will be a bunch of operators. Okay, so capital E of Xi. So now these, instead of being just numbers, now they're operators. And where are they acting? They're acting exactly on this Hilbert space H. And same thing on the D side. Okay, so yeah, for each I have a measurement, which is E of Xi. Yeah, so a measurement just means that the sum over X of EXI is equal to identity. Okay, so it's a direct generalization of the previous case where you make everything operators and the one is replaced by an identity. Yes.
Would something change if you wouldn't do the assumption that both Alice and Bob have the same Hilbert space? But
yeah, no, nothing will change. Yeah. So yeah, you could in principle say this H1 and this H2, but for simplicity, I just use the same H. Yes.
I understand that the IID assumption may break if you are on the setting, but doesn't it also affect, like in the case, affect the alphabet? Because, for example, when you look at classical variables being transmitted, you essentially consider a flip of, let's say, a bit, right? But don't you have, let's say, a larger error possibilities? Consider also maybe a phase or something. So you can have a bit flip, but then also a phase flip, and then.
So the error here now, okay. So the model here is that the noisy channel here is still a classical noisy channel. So for example, think of it as bit flips. But now this part, the entanglement, this is perfect. This, I don't consider it as part of my channel, or I'm not sure if I.
No, it wasn't about the entanglement per se, but I mean, this leads to trying to communicate by having physical resources, right?
Yes.
And in this case, you have, I don't know, some if you do it with neutral atoms or whatever,
yes,
you do it. These are physical systems, and you don't have bit flips, but you also have a phase error that you can have, and
yes,
then the definition of capacity
yes,
may change because you don't have an alphabet K, which would be the alphabet you're trying to communicate via bits, but you also have a phase that you communicate. So there's something you.
So yes, but so there's different. So here, I mean, you mean these things now have errors. So I feel you mean that in the entanglement itself, the state itself undergoes an error. Is that what you mean?
Yes.
Yes. Yeah. So this could be a very valid model where your entanglement is itself also noisy. It's not, you cannot prepare what you want, but you have some noise that affects it here. Here I'm looking at the more toy model where I'm assuming this part here, I do it perfectly. Okay, so here things are noisy, but on that side, everything is perfect.
It wasn't actually what I meant.
Okay, sure. Okay. So yeah, I mean, but this, if you start putting now that the computation is itself noisy, then this gets into the world of fault tolerance. So this is, but it's a little bit harder to study, but it's definitely something which is quite well studied. Okay, yeah, the setting of Shannon theory or communication is easier because you put all the noise in this channel and everything here and here is perfect. And so you can, in these cases, you can prove some theorems about the optimality. Okay, so yeah, okay, so here a very natural question from a quantum point of view is, okay, so now you can ask about the question without this resource, and so what is the optimal success probability you can achieve without this resource, and the optimal success probability you can achieve with this resource. Okay, And yeah, so this I call it P success probability quantum because with some entanglement. So yeah, so just let me write it more. Let's put the two optimization problems next to each other. Right, so here I've just rewritten it, and here I have written the version with entanglement. Okay, so now it's a much bigger optimization problem. So I optimize over possible Hilbert spaces, over states on the tensor product Hilbert space, over possible encoders and decoders. These are measurements.
Are you fixing the dimension of your Hilbert space?
No, it's arbitrary.
I see. So the H is just a dimension. So you have an integer. Because all Hilbert
Yes,
spaces.
yes, yeah. So I could have put here D, yes,
Yeah.
or CD,
Just
and yes, exactly. Yeah.
And now this X is still bits, or X is now vector space value?
No, X is the same. The sum here is over the same
Okay.
space. So and the I as well. It's from 1 to K as well.
It's just the encoder and the decoder.
Yes, it's just here. I mean, so everything. So it's just inside this. Here we have this product of numbers. Now it's a tensor product of operators and sandwiched with the state. Right. So I think you saw in this. I wasn't here, but in this morning's lecture, you discussed non-commutative polynomial optimization problems. No? That's tomorrow. Okay, so maybe this is a short intro. So yes, so okay, maybe I can mention some small thing because you mentioned the question here. So you can consider many variants here. So people consider sometimes infinite dimensional Hilbert spaces. Sometimes people look at the version where so just I put only the condition that these two operators commute instead of saying that they're acting on different tensor fragments. Okay, but this is something I don't know.
So when you say maximize eigenvalue.
So this is a number, right? Because so this is an operator on H, and this is an operator on H. And psi is a vector in H tensor H, and I sandwich it with them. So, but if you want, actually, you're right, in that this is, if you put the psi outside, you're doing the maximum eigenvalue of this operator. If you want, yes. If you want, you can forget about this psi and see this as just, this is a matrix, but of arbitrary size, right? And you want to optimize its, yeah, so I should have put supremum probably, but yes. Yes. Yes, here in the talk, I didn't want to get into the details of which variant I look at, but yeah, think of it for simplicity, just finite dimensional. Okay, so I optimize over finite dimensional Hilbert spaces. As I said, there's many variants and there's subtleties in this direction, but
the definition is not in set.
Oh, you mean the set of separable states? I think you meant separable Hilbert space, which are very different things, but very different. So you meant SEP in terms of separable as opposed to not entangled.
Yes.
Yeah. So yeah, here the state will definitely be entangled, otherwise it's useless, right? But yeah. So but two questions after. Okay, so there's of course one direction which is obvious, right? Which is that with quantum entanglement, you can do at least as good, right? So you can take the Hilbert space to be one-dimensional. Okay, so this is obvious. But the question is, can this program can the value here be strictly larger than the value here? Okay, so this is a problem that of course depends on W and K. And so the question is, are there channels for which this is bigger? And if this is the case, by how much? Okay, so this is the good. So it turns out, yeah, so there are some channels. You can construct some channels for which the success probability is slightly different, slightly higher with quantum. Okay, so again, without getting into the details. So this is a quite natural, simple channel. Just that maybe I get too much into the details here. So yeah, there is some channel for which you can achieve an advantage with entanglement. However, in the setting of IID channels, okay, you can ask in the specific case where now W is a product channel. Okay, my big W is a product channel, and I can ask whether this Shannon theorem still holds in the case where I have entanglement, right? So it could be, in principle, that the capacity grows when you have, because we saw that for some examples of channels, the success probability can grow higher. You can ask whether in Shannon's theorem, if you now allow the sender and the receiver to share some entangled states, whether this notion of capacity is still the right notion of capacity, or does it change? Okay, and it turns out that it does not change, right? So the asymptotic capacity stays. I mean, you have exactly the same formula. Okay, so of course here this side is obvious, the achievability side is obvious. The thing that you have to show is that if you're above the capacity, then even with entanglement, your success probability will go to 0. And this turns out it is the case. Okay, so yeah, so we have some evidence here. In some cases, it helps a little bit. In some cases, it does not help. And so, yes, what can we say something a little bit more general? So, for example, one natural question that when we started this project is, there be an arbitrary gap between can quantum entanglement allow you to have an arbitrary gap between to multiply the success probability by some arbitrary number, or it's not the case. And so here we showed in this result that it turns out that it's not the case. So this proves exactly that the advantage of entanglement is limited in that specific case. Okay, so maybe the simplest is set L equals K. This is the simpler. So if you set exactly L equals K in the statement, it tells you that if you multiply, let's read it here, simpler. So it tells you that the quantum success probability is at most the success probability without quantum resources multiplied by some constant factor. Okay, and so so how did we prove this result? So there, the important insight was to look at, the way we proved it is to look at the problem of computing this quantity from an algorithmic point of view. And as we'll see, so it's related to a very extremely standard problem in optimization. So this maximum coverage problem. And then if you consider a natural linear programming relaxation of it, then it turns out that it's also a relaxation for entangled strategies. Okay. So now if you can show that there is not a big gap between the problem itself and its linear programming relaxation, this would show that entanglement does not help by much.
Is there a conjecture, like what is the larger gap? Optimal function.
Yeah, this I don't know. So yes, I don't. So this is okay. So I don't know if this is type, in the sense that I don't have an example where you reach exactly this constant. Okay. We have it for some slightly larger class than the class of quantum strategies, the class of, for those who know, non-signaling strategies. Turns out that this is tight for non-signaling strategies. And for those who, so the non-signaling exactly corresponds to the linear programming relaxation. And so for that, it's tight. But for the quantum case, we don't know. I don't know the exact. Yes, so now what I wanted to do is to just get it to the so I have 1 hour, right? Is that okay? So yeah. Good. Okay, yeah, so just let me tell you how this is related to the problem of maximum coverage. Okay, so it's relatively easy to rewrite this problem. I mean, the reason I wrote it like this first is that you see that it's like when you make it quantum, quantum, it becomes very natural. Just you turn these e's and d's into operators. But actually, if you think about it, it's quite simple to see that this is achieved. I mean, the best way, I mean, that you may assume that this E is deterministic and the D as well, right? So in the sense that you will pick the X, the optimal encoder, as I put here. So for a given I, you will pick only a single X, right? There is not much use of making your encoder nor the decoder randomized. Okay, and then once you have this, you can construct your what we call typically a code, right? Which is just the image of your message set, right? Your message set is these numbers from 1 to k. Okay, the image of it under your encoder, which is now deterministic, is what I call the code C. Okay, and so then the success probability becomes the following optimization problem over now subsets of X. Okay, so I can write the optimal success probability as 1 over k times the maximum over all subsets of the inputs of my channel of some function of this subset. Okay. So yeah, and this function looks like this. So sum over y's of the maximum over x in C of W of 1 in X. Okay, so now this is a very well studied class of functions of a subset with a cardinality constraint. Okay, with a constraint that the size of the set is at most k. Yeah, okay, so it's maybe useful just to have a special case of a channel. So yes, so where on input X, right, you map X to an element chosen in Sx at random, uniformly at random, and assuming that all the Sx's are of size T. Okay, and in this case, you see that, so this is useful to make the connection to maximum coverage, right? So then FW of C is just, okay, some constant factor times the union over all X's in C of Sx. Okay, and so now you see that my problem here about maximum success probability is nothing but computing the maximum up to these factors 1 over t and 1 over k, which don't make a difference. So my function f of c is a union over all sets. Okay, and my sets are indexed by x. Okay, so I have this is the standard problem of coverage, which is I'm given a bunch of sets and I would like to pick k of them that have the largest possible union. Okay, this is called maximum coverage, super well studied problem in combinatorial optimization.
Question.
Yes.
For now, you're looking at POVMs on Alice's and Bob's side, right? Would something change if you look at generalized measurements? Or...
you mean what you mean by generalized measurements?
Measurements that affect the quantum state in a different way than it's being projected.
Okay. So actually, the only thing I look at is just the measurement outcome right now. So the post-measurement state does not have relevance for this problem. That's why, yeah, the POVM is the most general. Okay, so yeah, here I've just rewritten what I said. So this is the maximum coverage problem. It's a special case and uniform in the sense that all the sets have the same size. But yes, I have subsets of the same size, and I would like to choose a bunch of them, k of them, that have the maximum size of union. Okay, so yeah, as I said earlier, so this is the textbook problem in combinatorial optimization. We know that for that, the typical algorithm that's used is the greedy algorithm, which just you keep adding the sets that maximize union, your current union. And actually, this greedy algorithm works for an even larger set of functions, which are submodular functions. Again, I didn't write the definition of submodular because it's not particularly important here, but yes, okay, so this is a specific function which is submodular. It's a function of sets, which has this property of submodular. So yeah, this famous theorem which says that the greedy algorithm achieves this constant factor approximation for optimizing an arbitrary monotone submodular function, non-negative. Okay, and it turns out that, okay, so this is a nice algorithm. You can ask whether you can do better. It turns out you cannot do better. There's also a famous hardness of approximation result, which says that if you come up with an algorithm which achieves a factor approximation ratio which is better than that, then P is equal to H. Okay, so this is nice. So we now understand the complexity of approximating this problem, right? This problem of maximum coverage, and so because our problem is very directly related to it, this problem is almost the same as maximum coverage, then this is a problem that is hard to approximate within 1 minus 1 over E, but we can approximate it by a simple algorithm within 1 minus 1 over E. Okay, so but this does not quite answer the question that we had before, which is about how much entanglement helps.
Wait, sorry.
Yes.
What is E here in the problem?
E is the
length of
no, E is the 2.73. Yeah. How much is called that? Yes, exponent. Yeah, the exponent. Okay. Okay, so now back to the study. So quantum with entanglement, without entanglement. Okay, so the strategy now would be that we will find. So we have that the success probability with entanglement is lower bounded by the success probability without entanglement. But of course, as you've seen, this optimization problem is quite complicated, right? You have to optimize over all possible dimensions in principle. So this is very difficult to handle. Okay, so what we'll do is we'll come up with an upper bound on this, which is much simpler to handle. Okay, and it will turn out that this upper bound will be exactly the natural linear programming relaxation for this problem. Okay, and so it turns out that, okay, if you think a little bit about the maximum coverage or the maximum success probability problem, you can come up with a simple linear programming relaxation, right? So here you see that instead of, okay, for each element X, you either pick it or not pick it, you choose some numbers Px between 0 and 1, okay, and so you can fractionally take some elements X, okay, and this condition is just remember because here we had a maximum, okay, over X in C, and so this just plays the role of this maximum, these variables. I mean, this together with this. And so this, just if you think about it for a few minutes, you see that this is the natural linear programming relaxation for the problem P success. Okay, so yeah, here you have this by construction. And it turns out that we actually also have that the optimization problem with entanglement with these operators is also upper bounded by this linear programming relaxation. Okay, so this is a bit more for the people who have seen these games before. Otherwise, maybe you can forget about this, this comment. So actually, this linear programming relaxation actually corresponds exactly to the optimal success probability with something that in the quantum theory the community people call a non-signaling box. Okay, so so this is a box between. Maybe I say a quick word about it. No, so right. So think of a maybe so you can think that what Alice and Bob share, right? This entangled state together with these measurements, it takes on Alice's side there is an input and an output, and on Bob's side there is also an input and output. Let me just try to be consistent with the notation here. Here, this is the input, I, X, and Y, J. Okay, so you can just think, okay, here there's some box which is obtained by taking some shared entangled state and performing a measurement on Alice and a measurement on Bob. Okay, this gives you for any choice of state and measurements a conditional probability distribution, okay, of X, J conditioned on I and Y. Okay, so you can ask, what are all the set of such probability distribution you can obtain? Okay, in this way. This is actually a very complicated set. All right, this is even known to be undecidable, right? In this sense. But there is a very simple, like, upper approximation of this, which is so-called the non-signaling set. Okay, which is just saying what is this saying? It's saying that there is no signaling from that I cannot transmit information from Y to X, okay, or from I to J. Okay, so yeah, maybe I should have stressed this a little bit more. Is that so? Shared entanglement, it can help, it can boost a bit your success probability, but by itself, it will never allow you to communicate, right? So it's just a shared, it's a pre-shared state. It can even start before Alice and Bob know about the message they would like to transmit. So it does not allow you to communicate. Okay, so here, if you abstract this mathematically, it gives you this non-signaling condition. Tells you that, yeah, it's a certain mathematical condition which tells you that you cannot transmit from this side to this side. You cannot transmit information. And so these are simple linear constraints. And so that's why you get a linear program. And yeah, it's known actually that the set of non-signaling boxes this way is strictly larger than the quantum set. Yes?
What exactly is the second optimization problem hard to solve? Because like, does the SDP relaxation correspond to that not converge fast enough, or?
Yes, you could, of course, if you have seen the relaxation for non-commutative, yeah, you can use that definitely. Yes, but
fast, right?
no, I mean we don't have any. Yeah, so we know it converges. Okay, here you have to be careful about the notion that you look at. It to converge to the commuting, but even if we put that aside, like, so we don't know when it will converge, so we wouldn't know how to analyze this. Yeah, I mean, one of the big questions is, and actually we do know that in the general setting, right, the convergence can be arbitrarily slow, right? So, okay, it doesn't say that because here I'm looking at some specific kind of problems, not general games. So it could be that in this case it's faster, but in the general case, it's a hard question. Okay, so we get back to this.
So, Omar, can I ask something?
Yes. Sure. As Tony, or?
Yes. Sorry, it's here online. So I was wondering about the tightness of your condition, because you say that the bound was tight for no signaling, right?
Yes.
This is what you were saying before. So I was wondering if now you use the non-commutative polynomial optimization, whether you can get tighter bounds and then prove that the bound you have is not tight or something like this for some W's. Is it clear what I'm? So I understand. Let me see if I understand. So you go back to the previous slide.
Yes. You
study
okay,
relaxation. Oh, maybe I'm lost.
I think I see your, and actually here for this, in general, yes, so maybe I repeat the question. So the question is basically, can you, okay, so I think the question, if I understood it correctly, it's about, can you improve this the factor, like this factor 0.63, like 1 over 0.63 in the quantum case, right? So so we know that this this ratio cannot be improved if you replace this Q by non-signaling. Non-signaling is what I defined previously, but now the quantum set is strictly smaller. So can you improve this constant by now using SDP kind of techniques? And yeah, this is, I don't know how to do it. So I just know that for, okay, I know it just for one example. Okay, for one example of channel, for this channel, yeah, so as I said here, the success probability is without any correlations between the sender and the receiver is 0.833. With quantum entanglement, we know it's actually exactly equal to this because we have solved like level 1 or 2 of the hierarchy and we found this upper bound. Okay, and we know the non-signaling in this case is equal to 1. Okay. And,
of course, for some games you can get tighter bounds, but you want an amount that is holds for any situation, and then it doesn't help.
Yes. So it could be, I think as far as I'm aware, maybe this is the best ratio we have. So maybe there's a channel which does slightly better, but yes, so it could be in principle that one takes this general SDP and tries to round it in a way which is a bit better than the linear program and would get a better ratio. Yes, this could definitely be the case, but we don't know how to do it.
Yeah, sure. Okay, sorry. Yes, thank you.
Yes. Exactly. Okay, so just putting things again together, the only thing one has to show now is that this the ratio linear programming relaxation and the optimal success probability is this factor 1 minus 1 over E. And this is a relatively simple and standard argument from combinatorial optimization that you can do. Okay. And yeah, so I will not talk about it here. So yes, okay. So this is again just to sum up. So this is a case where using tools from, particularly it was combinatorial optimization, we can show that limitations of on how much entanglement can help at some tasks. And so one of my PhD students, former PhD student Paul Fermé, has studied this question but in slightly more general settings, like where you have 2 senders or 2 receivers, things like this. Okay, so if you're interested in this kind of question, his PhD thesis talks about that. Okay, so now, yeah, I wanted to, this is, okay, so I arrive at the end of the first part, and just to connect between the 2 parts that I will discuss. So remember, I said that these 2 are compatibility problems. You can see them as problem of deciding whether a given set of observations is compatible with quantum theory. So let me just comment on that briefly. So here I just rewrote the optimal success probability, okay, in the following way. So this is the maximum over all possible probability distributions in some set they call the correlation set. Okay, so it's like what I said here, but except now the first set is the classical set, if you want. It's just the convex combinations of product strategies. Okay, so here I have a function here and a function here. So it's a product of 2 functions, and just you take the convex combination of that. Okay, so this is what I call core here, correlations compatible with classical theory. And the quantum case is the same as that, except now you put operators, as I said before. So E and D are operators, and psi is a vector in the tensor product of the corresponding Hilbert spaces. Okay, so this is typically called the set of quantum correlations. And so I can see these two things as optimizing, maximizing some linear function over this set, okay, of, here we interpret it as conditional probability distributions. Here the correlation set, here the quantum correlations. Okay, and so what we showed in this it's just a reformulation. There is nothing new here. Is what we showed is that for these linear functions, which are of this form, right? So some noisy channel, and then so this delta. Remember, this delta I equals to j corresponds to the fact that the input message and the output message should be the same. So for linear forms, for linear functions that have this form, then there is a constant between these two. Okay, so is that we can approximate this thing efficiently. Okay, but a result which you might have heard of is that now if you allow this linear function to be completely arbitrary, right? So not of this specific form. Really, the important thing here is the delta I equals to j. This is the thing which is quite specific about this case. But now, if your linear function is arbitrary, then actually computing this becomes undecidable, right? And this is exactly the result in this very famous paper, MIP star equals RE, that came out a few years ago. Yeah, so it was exactly showing that in general, approximating a linear function over the set of quantum correlations is something which is undecidable.
What do you mean by approximate?
So within a constant. So it's even true within a constant, right? So yeah, for example, you want to decide whether this max is equal to 1 or less than a half. Even this is undecidable. It's not that because a bit before it was known that this, like computing it exactly, was undecidable, but the right question was approximated. It turns out to be also. Yes.
That I have to allow a.
Yes, exactly. To become arbitrarily large. Yes, exactly. Yeah, definitely. Because if we knew it's finite, then this would give an algorithm. Could just do a full search. Okay. Then are there any more questions? Because now I'll move to the next part, which is independent. Okay. Okay, so now let me move to another topic. So now this is about, it's again a problem, it's a very standard problem, even in quantum theory in general. It's, yes, so I would like to study the equilibrium states of a system of multiple particles. Okay, so let me start with the classical case first. It's simpler to study. So think of a system of n particles where each particle takes just two possible values. Okay, so each system, so it's composed of n systems, or here I call it particle, and each particle has a configuration which is just plus or minus 1. And I have some energy function, okay, which I'll denote h. So h is a function of my configuration and outputs a number, a real number. Okay, and then as is usual, so this is not a completely arbitrary function, because this would even take, this would be very costly to just specify such a function. But my function happens to be local in the sense that here for the Stoke, I'll assume that it's a sum of terms which only depend on pairs ij. Okay, so it's a sum over hij, zi, and zj. And the ground energy is just the minimum of this function. And the ground state is just a set of z1, zn that minimizes Okay, yeah, a typical example which is studied in computer science, for example, is, I mean, yeah, you can write all constraint satisfaction problems like this, but ones which are exactly too local here, maybe one of the most famous ones is max cut. Okay, so max cut, you take a graph, right, and you want to cut your graph into two parts such that there is a maximum number of edges that go through this partition. Okay, so this is very simple to write in this way. So yeah, so the plus minus one tells you you're on which side of your cut. Okay, so the one of the sides takes value plus one, the other takes value minus one. And so as a function here of a cut of your graph, this gives you its size. Okay, so I put a minus sign because here it's max cut, okay, so it's negative of that. Yeah, it's easy to verify that this formula just counts how many edges cross your cut. Okay.
Where's the cut?
So the cut is the so okay, maybe I do it from away.
In the right-hand side looks like just, you have all your edges, and you're taking that function.
Yes, but okay, so yeah, maybe I should have. So here, if both have the same value, if both have the value minus one, let's say, then you get 1 minus 1, you get 0, so it doesn't count, right? But if it crosses the cut, right?
There's no cut.
So I made so I have some elements that the minus one, minus yes, exactly. So cross here. This
I got it now.
okay, so this is a very famous NP complete problem, and has also a very famous approximation algorithm. Okay, so this is an example, but okay, in this talk, I won't be interested in classical constraint satisfaction problem, but in quantum ones. Okay, so now I want to study a quantum many particle system, the classical one. And so then the configuration space it will be a bit more complicated. It will not be just a bit string of length n. It will be a quantum state on bit strings of length n. Okay, so or it would be an arbitrary superposition of bit strings of length n. Okay, or in other words, it's a vector in C2 to the power n. Okay, so this is a 2 to the n dimensional Hilbert space. Okay, and so now the energy, right? So I have to define this energy function. Okay, so the energy will be given by a Hermitian matrix, and it will again be local in the same sense. So it will be a sum ij of hij, where I think of hij as acting non-trivially. So now it's an operator, right? So hij acts non-trivially. So you can think of it as identity everywhere except on the sides I and j. Okay. So simple special cases, classical systems. If you think of H as completely diagonal, right? Then this will be the same as classical systems that I described in the previous slide. Okay, and so the way I define the energy of a state psi, okay, is just by sandwiching H with psi. Okay, and so the ground energy is just the minimum over all unit vectors of H psi, or in other words, the smallest eigenvalue of H. Okay, and so okay, because I defined the max cut problem, there is a quantum version of it. So it turns out that okay, so the way it's defined, so here you see that it's defined like this. So I have 1 minus zi zj. So in the quantum case for qubits, natural thing would have been okay, so maybe let me introduce the Pauli operators first. Okay, so these are operators on two-dimensional space. Okay, so X is just doing a bit flip. So these, they play a very important role in quantum theory in general. Okay, so yeah, the most important is maybe Z and X. So Z is just a diagonal 1 minus 1. Okay, so if you don't put any X or Y, if you just leave Z, okay, so and here in my Hamiltonian, you just put Zi tensor Zj and you remove the X and the Y. It's easy to see because this will be diagonal, right? So this will be diagonal, so it corresponds exactly to max cut. Okay, so this corresponds. So if I remove X and Y, this exactly corresponds to max cut. But so in the quantum setting, it's natural to that. I mean, these they play these other Pauli operators X and Y. They play a similar role to Z, so it's natural to put all of them to the sum of them. Okay, so that's why this is called quantum maximum. So here, this is an identity now. Identity minus xi tensor xj, yi tensor j. Yes. Yes.
Don't you take tensor products and tensor products of these coordinates?
And there is identities everywhere else. Would be by
What's the connection with xi and x?
so xi is just this operator acting on I. And yeah, okay, so there's something I didn't specify here, I went a bit too fast, is that there's identities everywhere else, right? So this identity is an identity on all sides. This xi is an x on site I, tensor an x on site j, and everywhere else identities. Everywhere where I don't write, it's identity.
So the matrix A
Yes.
is a matrix of size 2.
Yes. Yes. Yes.
So that's the question. If I know x and y, let's say, but then I can still open double states because I feel like I should respond to the previous problem, the classical one, to consider additional double state.
Sorry, can you say that again? I didn't hear the beginning of your question. Can you say? So if you have only x, you mean?
If I know x, y, I didn't know that.
Okay. Yes.
This response to the first problem.
Yes.
But does it assume that the minimum is on the separable states? No.
No. I think it's overall. It's overall. It's so here your Hamiltonian will be completely diagonal. So the minimum eigenvalue will be exactly achieved on the minimum diagonal. I mean, yeah, you in the formulation of the problem in principle you can take entangled states and everything, but it will be.
But is there any reason on Pascal that generalize?
I'm not aware of any very deep reasons why it's called. It's similar in the sense that okay, you can write it in a way that makes it a little bit more similar. Here maybe it looks a bit superficial, but yeah, it's not. I mean, it has interpretation in terms of the quantum system. But yeah, no, it's not. It's just a natural quantum generalization of max cut. It's not a generalization per se because so you don't see max cut as a special case of it. But,
yeah. Say we solve this problem.
Yes. How would you help us for max cut or no in general?
Information theory. What? Say we had an algorithm that solved this thing, but what joy and happiness.
So I mean, the whole point of quantum simulation, right, is to this whole area of quantum simulation is that you're given a description of a quantum system, a quantum many-body system, either of this form or not necessarily of this form, right? And then to be able to determine its physical properties, right? And so the zeroth thing in terms of its physical properties is the ground energy. Is to be able to compute this quantity.
Right, but is this something that occurs in nature or?
No, this specific Hamiltonian, yeah, no, not really. Yeah, it's yeah, no, not really. It's not the most, especially even if it's on an arbitrary graph, this will not appear.
Sure, but even if we restrict, I'm perfectly happy with the answer that restricts to a class. You say, okay, if I'm on a whatever graph, end cycle, and I can stop this. This is related to something or other, a crystal.
Yes, no, as far as I'm aware, this quantum max cut is not directly related to any like important problems in condensed matter physics. Okay. Good. Yeah, so okay, I wanted to say something about the hardness. Right. So okay. So yeah, notice something that for these kinds of problems, they're not clearly it's not clear whether such a problem is in NP even, right? Because in NP you have to have a certificate that your energy is smaller than something, right? Here, what would be your certificate? Your certificate would be the state, but this is very large. How can you? It's not clear how to give it. Okay, but there is a natural analog of NP, which is called QMA, where the certificate itself is a quantum state. Okay, and so this problem, quantum max cut or the more general version, are in NP and are even are in QMA, and they're even QMA. They're complete for this class. Okay, and the thing I wanted to mention here is that there is even some undecidability results in this area. But of course, this problem cannot be undecidable. It's a finite matrix after all. So, if you look at infinite problems, like where you look at an infinite chain, for example, and you have that these Hij's are all the same, you repeat them, and you look at the infinite problem, then yeah, there's this also famous paper that says that in this case, problems which are closely related to the ground energy become undecidable as well. Yes?
You said that this has no implication in physical systems. But I was thinking if you have maybe like a one-dimensional system of few sides, and you put the system to superfluid state, let's say, then if you partition it, let's say in the middle, you'll find that this partition leads to subsystem A and B. You'll find the maximum entanglement. Sort of interpret the entanglement as cutting the most strings that go from particle to particle. Because you know, in superfluid, there will be correlations basically on every side. And if you have something like this, the maximum cut would be a measure of entanglement.
Oh, so you mean that this can be this notion can be a measure of entanglement? It could be maybe. I mean, yes, it could be. I mean, here I'm seeing it slightly differently in the sense that this is I don't see. So you see the value as some kind of max cut of some graph, as some entangled value of some graph. So, but okay, so maybe I can go in a slightly different direction. Is that so for this kind of problem here? By the way, this was only meant as an example, just to compute this max cut. There's nothing. I won't study max cut per se. It was only meant as an example, a simple example to the rest. But here, yes. So for this Hamiltonian, like entanglement plays a crucial role here. I don't know if this is what you meant, but so the state you would like to put ideally on every edge is a singlet state, like a maximally entangled state. Okay, so right. So unlike so the analog of 0, so in the previous in the classical case, you want to put 0 and 1 or sorry, +1 and -1 or the opposite. Here, what you want to put is the singlet state, like so. Like +1 -1, maybe I call it 1 0 plus or minus, I think, 0 1 minus 1 0. Okay, this is the ideal state that would keep your ideally you want to put all your edges in the state. But of course you cannot do that, right? Because of monogamy of entanglement, right? So it's not possible to have A entangled with B and A entangled with C as well, right? So there's this extra effect that comes into play, and that what makes it in some sense hard, but in some other sense also easy, in the sense that we can use like monogamy relations in order to put constraints on this problem. Good. Yeah. Okay. So roughly. So let me. Okay. So now the question is, let's just recap this. So what's my objective? Again, my objective is I'm given these. Think of these as 4x4 matrices, which tell me like side I and side J, they interact with this Hamiltonian. Okay, and okay, so you see that these HIJs they are 4x4 matrices. Okay, so they define a Hamiltonian, and I would like to be able to compute or to get approximations of this ground energy for this system. This is my objective, and so let me just let us just see. This is a standard thing, but it's I think you see is that the ground energy problem, you can see it as a compatibility problem. Okay, so that some sets of numbers are compatible with the global state. Okay, so let me say that. So let me take a state, quantum state psi, so a pure vector psi. And I will consider the following function. Okay, so it takes as input a matrix. So A is a matrix. It's an operator on my Hilbert space, on the big Hilbert space, and it's just A sandwich with psi. Okay, this is called. I might use this. So I put here. So it's an expectation value of A. Okay, so what does this function satisfy? Okay, function of observable. Okay, so it satisfies the following condition. So if I put the identity here, right? So this one here is an identity. It gives me 1. Okay? And also if I put A dagger A here, or A star A, so that this is a conjugate transpose. Okay? A adjoint A is non-negative, any A. Okay, in the set of matrices over my Hilbert space. Okay, and so let me just now I rewrite the ground energy problem. Right, so it's the minimization. Of course, it's just the minimization over all possible states, over all possible psis of H. Here I put instead of A, I put H and sandwich with psi. Okay, but the thing that I would like you to observe here is that because my Hamiltonian is local, right? So the H that I will plug in here is the sum of HIJs, right? Then you see that this here this will only depend on HIJ, which is sandwich with psi. Okay, and this only depends on. Or maybe I don't want to use the language of partial traces. So so you see that that's why I wrote it like this. So you see that this only depends on the value that my functional. So this omega is a function of a valid state takes on Hij. Okay, so in other words here, so I have just rewrote my problem as a minimization over all. These are numbers now, Xij's, in the set C, and then I take the sum of Xij's. And what is the set C? The set C is just the set of possible tuples, omega of Hij, when I go over all possible Ij's. Okay, so in other words, I only need the value of omega on local matrices Hij. Okay, But of course, here the difficulty, I've not done much here, but I have just concentrated the difficulty. So this is a problem that looks small. So this is a small dimensional thing, and the xij's are small dimensional, but I have put all the complication in the set C. I've concentrated all the complication in the set C. And what is the set C? This is a set, it's the set of values that a valid state can take on local matrices. But that I need that they're compatible with the global state. Okay, this is the hard thing. And so for people who are come a bit from a quantum background, so this corresponds to variants of this are sometimes called the quantum marginal problem. So I'm given marginals of some state, and I want to know whether there is a compatible global state that's compatible with these marginals. Okay, so so what we would like to do is to get a good characterization of the set C if we want to solve this problem. So
when I think of marginal, I'll think of that's problem in representation.
Mhm.
I don't see any reference.
yeah, no, there is no. Because I think you maybe think of the quantum marginal problem. I think you probably think of the one with 3 parties where it's globally pure, right? Yes. So here it's a slightly different one. I'm on n sites and I have like overlapping parts. So it's a slightly different. I mean, yeah, there might be also some representation theory there, but it's a slightly different version. Good. So, okay, so the natural relaxation, and this has been known for a while, for this problem, right? So I have just rewritten things. So I have just rewritten the ground state problem again. So I minimize with this notation of omega, right? The valid state omega. So I just evaluate omega on H. Think of it as sandwiching H with a vector, such that this corresponds to a valid state. And corresponding to valid state means it's just the fact that omega maps to 1, and it's positive in the following sense. Sorry, I changed the between star and dagger, so it's supposed to be the same everywhere. Okay, so a very natural relaxation of this is to say that okay, so what is difficult in this optimization problem? What is difficult to impose here? Difficult is that imposing this is the same as imposing a positivity condition of a 2 to the n by 2 to the n matrix. Okay, so this I cannot do, but what I can do is that I can take a smaller algebra here and just impose positivity there. I can take just a smaller set here, okay, and say that I impose only this positivity. So this will give me a lower bound. Okay, so yeah, so here I just describe this. So I say that if I take here the subspace of matrices spanned by matrices acting on at most k qubits, then I get the following relaxation. Okay, so I put less constraints. Okay, so this will give me a lower bound, and so this gives me a hierarchy as I increase k.
Is it the same as A matrices?
The
Classical. Instead of E is default, you relax all the stuff like, well, you apply some x transpose by x as only A non zero.
Yes, it corresponds to that. Yes, yeah. This is the version. Yes, I wrote, but this is probably standard for you. I mean, this last constraint, of course, can be expressed as a positive semi-definite. Okay, so this is all standard, and it was known for, I mean, quite old from the people in this matter and quantum chemistry, and then it was also discovered by Geronimo Navasquez Nassim in a more general framework. Okay, so yeah, this gives me convex relaxations indexed by K. Skip all of this, but so yeah, I wanted to talk a little bit about results on improving these cuts using notions of quantum entropy. Okay, I think I'll skip it. Skip that as well. Yeah, maybe, okay, maybe I'll briefly just talk about this slightly more general problem, which is, okay, so the problem that you would actually like is not only computing the ground energy, but also computing physical properties of the ground state, right? So imagine you take a physical system that you're interested in, and you would like to know its physical properties, okay? So some observable, A, evaluated on the ground state. Okay, so not necessarily only the energy, but also an arbitrary observable. And so, what can we say about this problem? Okay, so this is what we studied in that paper. So, okay, so it turns out that the value of an expectation, the expectation value for the ground state might not be unique because you can have multiple ground states. Okay, so that's why I will define an interval. Okay, so between the minimum expectation value and the maximum expectation values. And so, yes, what we do in this paper is we give bounds on this expectation value. Give a hierarchy of semi-definite programs for computing these expectation values, approximately these expectation values. Okay, so let me skip here. And one implication of that is that we show the decidability of this problem. Right? So, which was, okay, given a Hamiltonian, okay, so this is a local Hamiltonian H. So this is a small matrix. Think of it as a 4x4 matrix. And you put it on the infinite grid. Okay, so this gives you an infinite Hamiltonian. And you want to know whether the expectation value is bigger than A or smaller than A. And so we give a decision algorithm for that. And so one reason I wanted to mention that is that this seems to contradict with some recent results, which showed that like a slight reformulation of this problem is undecidable. Okay, but it turns out that the formulations are slightly different, so that's what avoids the contradiction. Okay, so I have some numerical results. Let me skip it. So maybe I quickly finish with some open problems. Okay, actually. Okay, so maybe I mentioned the last one. So, I mean, so so these are classical algorithms for these quantum simulation problems. And so I think one interesting avenue is to use these as a benchmark for now really genuinely quantum algorithms for these problems. Okay, I will stop here.
Thank you. Very tight schedule. In this very minute, we're supposed to start the next talk. So we postpone the questions to after that. And we start now with the last talk of today of École, former student.